get started with our class today. First, let me make an announcement. I have placed some new material into the LMS website. So if you go to the LMS website for the course, I've added the lecture slides in PDF format. These are the lecture slides that we see during the lectures. I've also added for each lecture, I've added some required reading from the textbook. So for instance, for our last lecture, required textbook, you can find it here. So it will be 4.3 and 4.4 from the textbook. For each lecture, you will find such required reading from the textbook. So once you listen to our lectures during these classes, and then if you have some questions, you can go over the PDF slides that I provide. You're also, in addition to these, you're also expected to do the reading necessary from the textbook. Okay? So these are more, in the textbook you will find more detailed descriptions of the topics that we cover. Any questions about this? Any questions about the administration of the course? Can everybody still hear me fine? Can you all still hear me clearly? So, Betty, can you hear me fine? Okay, so if there are no questions regarding the administration of the course, as I said before, from time to time, try to check the LMS website for the course and try to follow the required reading material from the textbook and also go over the PDF slides. And finally, the recordings for these lectures, you can find them in the Teams website or in the Teams application. Okay, I don't know how to fix the issue with the microphone because I don't have any other microphone. Does everybody have the same problem that it is difficult to understand me? Can you all understand when I talk? So Berkay seems to have a problem. Does everybody have the same problem? Is it completely... So can you understand when I talk or can you not understand at all? So let me try turning off the camera. Maybe it's taking some... How is it now? Can you hear me better? Is there still the same problem? Can you not understand when I talk? When I talk, do you understand or not? Okay. So, if we have resolved this issue with the microphone, let's get started with our lecture. Let me share the PDF slides. Can you all see the PDF slides that I shared? Okay, so yesterday we started talking about solving recurrences, and we have talked about mainly a method that we can use, basically a number of steps that we can use to solve recurrences. So remember that recurrences are basically definitions of functions. Those functions most of the time are the running time functions. So the definitions of functions that are defined recursively. How do we come up with these recursive running time definitions, running time function definitions? We basically analyze code or the description of some given algorithm. If the algorithm is recursive by nature, then it's easy to write down or to describe its running time function TON recursively as well. So that gives us a recurrence relation that describes the running time of some algorithm. Now, looking at a recurrence, it's hard to tell whether the given running time function is large, asymptotically large or not. So the next step is to find out an open form formula or a theta or the same function in theta or big O notation. And the way to do that, the steps that we described to do it in our previous class was to first of all find out a guess regarding a theta bound or a big O bound for the given recurrence. And that guess we can construct using the recursion tree method. Okay, so in the recursion tree method, we basically expand the given TON until we have a recursion tree consisting only of terms in open form, and then we try to guess basically the sum of all the terms in the given tree. If we can do that, then we have a big O bound guess for our function, and then the next step usually is to formally prove that that bound is correct using mathematical induction. In this class, we will see a second way that we can use, a second method that we can use to find out a theta bound for a given recurrence. This is called the master method or the master theorem. But different from the previous method, which was basically based on guessing a bound based on recursion tree, this one we will be only able to apply to certain types of recurrences. So this theorem we will be able to apply to recurrences of this form. Tn equals a times t of n divided by b plus f of n. Okay, in such a recurrence, a is assumed to be greater than or equal to 1, b is greater than 1, so these are some constants, and f(n) is some asymptotically positive function. So note that this method will be an easy way to solve a recurrence, but as we said before, it will be only applicable to these types of recurrences. For instance, we won't be able to apply master method to a recurrence of this form, because, okay, we have a constant a which is equal to 2, but inside b, inside t, we don't have a term that is similar to n divided by b. Okay, we have a function in the form of a square root of n. So it's not in the form n divided by b, which means that we cannot apply master theorem to easily find for this TON. But we could apply it to a recurrence of this form, for instance, because we can write this recurrence more simply as 2 times t of n divided by 2 plus 5. So such a recurrence would be similar to this definition. Let's see if this definition is in the format that we want. A times t of n divided by b. In here, a is equal to 2 and b is equal to 2 as well. A times t of n divided by b plus some function f of n. In this case, our function f of n is simply a constant 5. So such a recurrence relation would be in the format that we require, that where we can apply the master theorem to solve for this recurrence Tn. Okay, so let's continue. If our recurrence is in this format, we will basically have three cases that we will check. In all the cases, when we want to apply the master theorem, we basically compare two functions. We compare this f of n, so all the time when we apply master theorem, we will compare f of 1 versus a second function will be this function, n to the logarithm b base a. So f of n versus n to the logarithm b base a. In simple terms, when we compare these two functions, whichever one is bigger, we will say that t of n is theta of that function. So for instance, if n to the logarithm b base a is asymptotically bigger than f of n, which is represented by this first case, this first case says that f of n is upper bounded by n to the logarithm b base a, and we even subtract some small epsilon from this power logarithm b base a. So if n to the logarithm b base a is asymptotically greater than f of n, then we take the larger one. Tn is theta of n to the logarithm b base a. From the opposite, if f of n is asymptotically larger than n to the logarithm b base a, check condition 3, f of n is omega of n to the logarithm b base a, and we even add some small constant epsilon to the power logarithm b base a. This basically says that f of n is asymptotically larger than n to the logarithm b base a. And as we said before, among these two functions, whichever one is larger, whichever one is asymptotically larger, we will say that t of n is theta of that function. In this case, since f of n is asymptotically larger than n to the logarithm b base a, we say that t of n is theta of f of n. Finally, if these two functions, when we compare them, they grow equivalently. Basically, check this out, check this second condition. F of n is theta of n to the base a. Asymptotically, they grow at the same rate. F is equivalent to n to the logarithm b base a. If this is the case, we will take any one of them. It doesn't matter which one, since they are bounded by the theta relationship. Take, for instance, n to the logarithm b base a and multiply it with a log n factor. So t of n will be theta of n to the logarithm b base a times log n. Is the definition of the master theorem clear? Any part that we need to repeat regarding the definition of the master theorem? I don't see any questions, so I will continue. Let's continue with some examples where we apply master theorem to find a theta bound for a given recurrence. Equals 9 Tn divided by 3 plus n. Let's check that this recurrence is in the format that we want. Because if it is in this format, then we can easily apply the master theorem to solve for the given function Tn. So a in this case is 9. So a is 9. In this format, we have T of n divided by b. b in this case is then 3. And at the end, we have a function f of n. In this case, our f of n is n. So it is in the format, it is in this general format, Tn equals a times T of n divided by b plus f of n for constants a, b, and asymptotically positive function f of n. It is in this format. This means that we can apply master theorem quickly and easily find a bound for T of n. To apply master theorem, remember, we will be comparing two functions, f of n, which is n. So in this case, we will be comparing n versus, so this is f of n versus the second function was n to the logarithm b base a, n to the logarithm, our b in this case was 3, logarithm 3 base a as in this case is 9, logarithm 3 base 9. Note that logarithm 3 base 9 is 2, so this function in here is n squared. So we are comparing n versus n squared. Since n squared is larger, so we have then case 1, because f of n, which is n, is big O of upper bounded by n squared, and we can even subtract some small epsilon from that. If that is, remember we said that T of n will be the larger one, which in this case is n squared. T of n is theta of n squared. So we find out that T of n is theta of n squared. Is this example clear for everyone? Notice that we mainly did two things. We started by checking first whether our recurrence is in the format that we want. If it is, we continue. We compare two entities, the function f of n versus n to the logarithm b base a. Whichever one is bigger, we take that one. Tn becomes theta of that function. Let's see another example. Tn equals 2Tn divided by 2 plus theta of n. We first need to check whether we can apply master theorem to this recurrence definition. To do that, we need to check whether it is in the format, in this format that we want. Tn equals a times T of n divided by b plus f of n. A in this case is 2, b in this case is also 2, and our function f of n is theta of n. So everything is fine. The format of this T of n is fine with respect to the format that we require to be able to apply master theorem. To apply master theorem, remember we were comparing two entities. F of n, this is in this case theta of n, so we are comparing theta of n versus n to the logarithm b base a. In this case, n to the logarithm b base a will be n to the logarithm 1 base, n to the logarithm 2 base 2, which evaluates to 1. So this is n to the logarithm b base a, for this case is n. F of n is also theta of n. So both of the functions we compare are equivalent. This means that the second case of the master theorem applies. F of n is theta of n to the logarithm b base a. Remember that if the functions we are comparing are equivalent, are bound by the theta function, then we take any one of them and multiply it with the log n factor to find Tn. So Tn will basically be, take any one of them, take n multiply it with log n factor. So our Tn is theta of n log n. Does anybody remember this recurrence from somewhere, from our previous classes? For which algorithm did we come, while analyzing the running time of which algorithm, did we come up with this recurrence to denote its running time? Does anybody remember? So I don't see any replies, maybe. Okay, so merge sort. You're right, Asena. So while analyzing merge sort, we have come up with this recurrence to describe its running time. Remember that in our previous class, to find a bound, to find a theta bound for such a recurrence, we used the longer method, which consisted of first drawing the recursion tree for this recurrence, and then summing up the terms in the recursion tree to find a guess for our bound, and then formally proving that our bound is correct using mathematical induction. But note that with the master method, with the master theorem, we don't have any further steps. This is it. If our recurrence is of this format, we will simply check these three cases. Whichever one applies, we will immediately find out our T of n, find out a theta bound for our recurrence T of n. Okay, so applying master theorem, solving a recurrence using master theorem is quite easy. Let's see yet another example. Tn equals 7 times Tn divided by 2 plus theta of n squared. In this case, our constant A is 7. Our constant B, remember that the format was A times T of n divided by B plus f of n. So our B is 2. Finally, our f of n is theta of n squared. And remember, we will be comparing two functions, f of n, which is theta n squared, versus n to the logarithm b base a, which is n to the logarithm 7, n to the logarithm 2 base 7. Okay, now if we compare these two functions, okay, obviously this one is larger. N to the logarithm 2 base 7 is asymptotically larger than f of n. Remember our rules for the master theorem. Whichever one is asymptotically larger, if one of the functions we are comparing is asymptotically larger, then we immediately say that Tn is theta of that larger function. So we say that Tn is theta of n to the logarithm 2 base 7, since n to the logarithm 2 base 7 is asymptotically larger than theta n squared. Because this power, logarithm 2 base 7, is greater than this power, is strictly greater than 2. Let's see another example. Tn equals Tn plus 2 plus theta 1. If you remember binary search from your previous classes, from your data structures course for instance, you will remember that the running time of binary search can be described with this function. Why? Because the main idea in binary search was compare our key value against the middle element in here. Assume that this array is sorted and we are searching for some value x. We compare x against this middle value. We do one comparison, theta one time, and if x is smaller than this value, then we recursively solve the problem for this left half of the array. Otherwise, if it is bigger, we recursively search for x in the right half of the array. But in either case, we run our binary search algorithm on an input of size n divided by 2 only once. So this will be the recurrence that describes binary search algorithm. Search left half of the array, for instance, and a constant number of comparison operations. Let's see if we can apply master theorem to this recurrence to find a theta bound for this T of n. Our A in this case is hidden. Our A in this case is 1. So there's an implicit 1 in here. Our A in this case is equal to 1. Our B in this case is 2. And our function f of n is theta of n. F of n is theta of n. So everything is fine with respect to the conditions that we require from the format of a recurrence where we can apply master theorem to solve the recurrence. It is in this format, a times q of n divided by b plus f of n. Okay, now we compare f of n, so which is basically theta of 1, sorry, so this is theta of 1. We compare theta of 1 versus n to the logarithm b base a. So b in this case is 2, a is 1. So n to the logarithm 2 base 1. Logarithm 2 base 1 evaluates to 0. So this is n to the 0, which is 1. So theta 1 versus theta 1. We see that these two functions are asymptotically equivalent by theta, which means that we need to apply case 2 of the master theorem, which says that if those two functions we are comparing against are equivalent, then take any one of them, take theta 1, multiply it with log n factor. So our T of n will be theta of log n. Let's see one last example. Tn equals 4Tn divided by 3. Our A is 4 and our B is 2 and our function f of n is n cubed. So it is in the format where we can apply master theorem. We will be comparing f of n, which is n cubed, against n to the logarithm b base a. So n to the logarithm b is 2, a is 4, logarithm 2 base 4 is 2, so n squared. We will be comparing n squared versus n cubed. Obviously, n cubed is asymptotically larger than n squared. In that case, master theorem tells us that T of n will be the theta of the larger function, asymptotically larger function. So T of n will be theta of n cubed. Okay. So, are all the examples that we have seen so far regarding how we apply the master theorem to solve or to find a theta bound for a given recurrence Tn, are they all clear? Do you all understand how we can apply master theorem to solve for a recurrence? Okay, so if it is all clear, let's start with a new topic. We will see yet another sorting algorithm. It will be called heap sort. So somebody has a question. Vlad has a question. So, regarding which case you need to use, which case will apply, depends on the recurrence relation that you are working with. You will be, as we said before, just to summarize, so if you don't want to get into too much details of these three cases, in simple terms, you will be comparing f of n of your recurrence, which is basically the last function added to your recurrence. So you will f of n against n to the logarithm b base a. Okay? If one of them, say f of n, is asymptotically larger than the other one, then we will say that t of n is f of n. On the other hand, if n to the logarithm b base a is asymptotically larger than f of n, then we will say t of n is theta of n to the logarithm b base a. Basically, for those two cases, we can combine them into the following simple sentence. Compare f of n against n to the logarithm b base a. Whichever one is asymptotically larger, Tn will be theta of that large function. If they are equivalent, meaning that if f of n is theta of n to the logarithm b base a, this means they are asymptotically equivalent, then take any one of them and multiply it with a log n factor. That will be the theta bound for our t of n. Is this clear, Vladislav? Okay, if you don't have any further questions regarding the master theorem, let's go on to the next topic. As we mentioned earlier, we will now see yet another sorting algorithm. Remember that so far we have seen two sorting algorithms in this class. One of them was insertion sort. Does anybody remember the running time of the insertion sort algorithm? The running time requirements of the insertion sort? So we have seen insertion sort, and a second sorting algorithm was merge sort. So far we have seen these two sorting algorithms, insertion sort and merge sort. Anybody remembers the running time analysis of insertion sort? For insertion sort, there is an answer of n squared. Remember that for this specific algorithm, insertion sort, we made two types of analysis: worst case and best case. For its worst case, we said that the running time of insertion sort in the worst case is theta of n squared. What does it mean to mention a theta bound while analyzing some algorithm in the worst case? It actually means two things. One is that insertion sort has a running time big O of n squared. Since it is big O of n squared, it means that no matter what inputs you give to this insertion sort, it will not require more time than n squared. But since we are mentioning theta, we are actually saying a second thing as well. We are saying that the running time of insertion sort in the worst case is also omega of n squared. Saying that insertion sort's worst case running time is omega of n squared means that there exists some input instance such that insertion sort requires at least n square running time. That's why, since worst case running time of insertion sort is both big O of n square and also omega of n square, we say that the worst case running time of insertion sort is theta of n square. But we also did a second type of analysis for insertion sort. So this first one was worst case analysis. And the second one was the best case analysis of insertion sorts. What can we say about the best case running time of insertion sort? Does anybody remember that? N. Yes, Vladislav, it is N. Is it big O of N or big omega of N or both of them? Both of them means theta of N. Which one? Okay, Faizenur says the best case running time for insertion sort is big O of N. Can we also say big omega of N? Yes. So insertion sort has a running time, best case running time, that is big O of N. What does it mean to say that insertion sort has a best case running time of big O of N? It means that there exists some input instance such that insertion sort requires at most linear. And we know that there exists such an input instance. For insertion sort, if the input instance is already sorted in increasing order, consists of a sequence of items in increasing order, then that's the best case. And for that best case input, insertion sort doesn't require more than n time. That's what it means to say that insertion sort has a best case running time big O of n. And it also has a best case running time of omega of n. Can anybody tell me what is the exact meaning of that? Basically, what is the exact meaning of saying that insertion sort has a best case running time of omega of n? So basically for this one we said it's also worst case is both big O of n square and omega of n square. We talked about their meanings, both of their meanings for the worst case. And for the best case, we are also saying that insertion sort has a running time of big O of n. We just explained its meaning. But what does it mean to say that insertion sort has a running time of, a best case running time of omega of n? Can anybody tell me this in one sentence? So let's repeat the analogous notation for the worst case. For the worst case, if we are saying that insertion sort has a worst case running time of big O of n squared, we mean the following, that no matter, so big O for the worst case applies to the description no matter. So you can remember it like that. No matter what input you give to insertion sort operation, it won't take more than n squared. Okay? So big O for the worst case analysis means no matter what inputs. On the other hand, omega for the worst case analysis means there exists. So there exists some worst case input instance for insertion sort such that insertion sort requires at least n squared. Okay? So while doing a worst case analysis, talking about big O means no matter what input you give. And talking about big omega notation means there exists some instance that requires at least this much. For the best case analysis, it will just be the opposite. Okay, so for the best case analysis, when we say insertion sort has a best case running time of big O of n, we mean that there exists some input, some good input instance for insertion sort such that it requires at most n time. So big O for the best case analysis means there exists some instance. On the other hand, omega for the best case analysis has a meaning that applies to everything. So we basically say that for any input instance for insertion sorts, it should take at least n time. Okay? Any input instance to insertion sort will require at least n time. Is this discussion the distinction between big O and big omega while talking about worst case and best case analysis clear? So that's why we say that insertion sort has a worst case running time of theta of n squared, since it is both big O n squared and big omega n squared, and insertion sort has a best case running time of theta of n because it's both big O of n and also omega of n. Any part that we need to repeat in this discussion? Is this discussion clear for everyone? Can you all still hear me? So for a while ago, Faizenur has written something saying omega shows the best case, big O worst, and theta shows the average case. So I just described in detail. This is actually not true. So when you talk, big O is just an upper bound. So you can talk about some worst case and use big O notation, as we have just seen in here. When we are talking about the worst case, we are using the big O notation and also omega notation. So these notations, just by their definition, don't have to do with analyzing worst case or best case. The meaning of big O is an upper bound. The meaning of omega is a lower bound. And the meaning of theta is captures both of them. It's a theta bound. But while we're making a worst case or best case analysis, although we can talk about both of the notations of big O and omega, their meanings will be different. As we said before, if I say that insertion sort has a worst case running time of big O of n squared, what I mean is that there exists no input that will require more than n squared. For all the inputs, for any input you can think of for insertion sort, it will be requiring at most n squared running time. On the other hand, we can still talk about omega in the worst case, but the meaning will be different. When we say that insertion sort has a worst case running time that is omega of n squared, what we mean is that there exists some input instance, some worst case input instance, such that insertion sort requires at least n squared running time, since omega means at least. Okay, so the meanings will be different, but we can talk about big O or big omega or theta in all these different types of analysis: worst case, best case, or average case, which we haven't talked about yet. Was this clear for you, Faizenur? Okay, finally let's talk about, we have also seen the second type of the algorithm that we have covered was merge sort, and we have seen that for merge sort we don't have any worst case or best case scenarios. In any case, no matter how the input, what the input is, the running time of merge sort is theta of n log n. We don't do separate analysis for merge sort because no matter what the input instance is, this will be the running time of merge sort, theta of n log n. Is everything clear regarding our summary of the sorting algorithms we have seen so far? This is just to summarize the running time analysis of the two sorting algorithms we have seen so far. Any questions about this summary? Anyone? Is everybody still listening to the lecture? Okay, let's give a 5-minute break, okay, and then we will come back to our lecture again to this meeting. I won't shut off the meeting, I won't turn off the meeting. Let's get back to this meeting after 5 minutes at, let's say, 2:55. Let's join the meeting again, and then we will continue with a new type of sorting algorithm, which is called heap sort. Okay, see you in 5 minutes.